welcome to the JAX introduction tutorial. This is the first year that we're doing this tutorial, yeah, don't judge me too hard. But yeah, the reason I wanted to do a JAX tutorial is because I think JAX is more and more represented in astronomy code. I think probably you're all here because you've heard of JAX before, or maybe you were curious, but before I actually learned about JAX, I had sort of heard of it in various circles, and I heard that it was fast and it was good for parallel programming, but I didn't really know anything about it. So this is going to be a very brief introduction to JAX. I don't think that I'm a JAX expert. I would say I'm conversational in JAX. So if you ask really hard questions, I'm not going to be able to answer them. So part of the reason I wanted to make this tutorial is because I want to understand JAX better, and a lot of the development that I have planned for myself over the next year uses JAX. So hopefully this tutorial will be even better next year when I have more experience. Yeah, so we're going to talk about the structure of the tutorial is we're going to talk about just-in-time compilation, and I'll sort of briefly define what compilation is and specifically what just-in-time compilation is. I'm going to talk a little bit about how JAX works and how it doesn't work, and in particular some things that might trip you up when you start using JAX. I'm going to take you through two useful functions, jax.grad and jax.vmap, which are picked because they can significantly help your performance of your code in a lot of cases. And then I'll finish off about running JAX on GPUs and TPUs. And the spoiler of this is that it's very easy, and that's why people like using JAX, is that you basically don't need to write any additional code in order to run JAX code on GPUs and TPUs. So let's take a moment to appreciate the meme. No chuckles? Aw. Thanks, guys. Makes me feel better. All right, so let's talk a little bit about just-in-time compilation. So can I get a show of hands? Who has heard the word compilation before? Okay, so most people have heard of it before. I'm going to assume that the statistical sample in the room also represents the Zoom sample. Okay. So I'll briefly go over what compiling is. So compiling is something that a computer does to translate the code you've written into code the computer can understand. So there's many, many steps. There's lots of complexity in this. The thing that we need to know for this is that Python's not a compiled language. That doesn't mean that it doesn't compile your code. Every time you run code on your computer, it has to be compiled. But it does mean there's not a separate compilation step. So if you've ever coded in C or C++ or Fortran, there's a whole separate compile step where you run something on your terminal, it creates a binary thing that can be executed, and then there's a separate step of actually executing the code. Compilation also involves a lot of error checking. One thing that's sort of a fun little fact that helps you understand what compilation is a little bit better is that in Python, syntax errors are discovered at the compilation step. So if you've ever noticed that you get syntax errors very fast when you run Python code, that's because it's not actually running the code. It's just going through that first step of compiling before it runs into that syntax error. An attribute error, for example, which is when you try to access an attribute of an object that doesn't exist, that's discovered at runtime. So that'll take a little bit longer for your code to actually run into. So JAX looks like Python code. And in particular, that's why I made this meme, is because you can basically just sort of use it naively as a drop-in replacement for NumPy. But under the hood, this stuff is being done very differently. So understanding what JAX is doing, even at the basic level under the hood, will help you run much faster code. Actually, a really common thing when people start running JAX code is they're like, this doesn't do anything. It's actually slower, or it's not as good. And that's basically just because it's easy enough to implement JAX functions that you can very easily just rewrite all your code as jnp dot whatever without actually speeding it up, because you're not understanding what the code is doing under the hood. Yeah, so one thing that is important to understand that that affects the way that JAX runs code is that JAX is compiling things in a special way, which we'll talk about in a sec. So the way that JAX is compiling stuff makes it easier for stuff to be run, but that compilation step also takes time. So you really only want to use this compilation, this special compilation that JAX does, if the time to actually run the code after you've compiled it will save you enough time relative to the amount of time it took to compile it in the first place. So overall, you should consider using JAX if you need to multiply large matrices many times in a row. And this is in particular what JAX was designed to do. JAX was designed at Google for machine learning. Or if your code is doing a lot of numerical operations in parallel or can be easily extended to do so. So generally, when you're thinking about large data sets or just running a lot of parallel computations, JAX is a really good thing to do. On the other hand, the embarrassingly parallel problems, which we heard about a little bit last hour, which include running the same analysis script on different CPUs, those are not going to be super amenable to JAX. So that would be a good thing for Python parallelism or running something with MPI. Okay, so let's get into just-in-time compiling and what JAX is actually doing under the hood. So JIT, or just-in-time compiling, means that the compiling is done at runtime, meaning that when you press the run this code button, the code is actually going to do the compilation very quickly and then execute the code all in one step. So JAX is fast because it compiles things first into this intermediate language called JAX expression, or JAXPR, and then that is compiled to XLA, or accelerated linear algebra. So XLA is a compiler, and it's a very, very fast and very optimized compiler for linear algebra operations. So there's a ton of there could be many hours of lessons on how XLA actually works and why it's faster. But basically, all you need to understand for now is that JAX compiles things with this XLA processor, and that enables it to do these things very fast. So first step, when your computer reads in your Python file with JAX in it, is that it takes all the stuff that can be compiled into XLA and it compiles it and then it runs it. So again, the sum total of those things is the stuff that has to be faster, not the individual steps. So the way that JAX produces first the intermediate thing, the JAXPR, which is then compiled with XLA, is using a process called tracing. So I'm going to give you a little example to show you how this works. Not give away the answer. So take 1 minute, take 30 seconds to just look at this code. Great. Okay. So what this is doing, this is called a decorator, if you've never seen this before. At the top, this jax.jit. And what this does is that it marks this function as something that we want to be just-in-time compiled. So when the processor is running through the code, it'll run into one of these jax.jit and say, okay, this is something I'm going to try to translate into JAXPR, then into XLA, then compile with XLA. So we've got a very simple function where we're just adding one to the input array, element-wise. So we're going to call it first on an array with just 0 in it. You'll also notice that we're using a NumPy array. We're using something that looks like a NumPy array, but is actually defined with JAX. So it's just jnp.array. We're then making a subsequent call with an array of the same shape. And then we're going to make another call with an array of a different shape. So you'll see a difference in behavior because when the first time that JAX runs a code with a particular combination of function and input type and shape, it will compile it, but then it can save that like compiled thing executable for later. So it doesn't need to recompile it every time. So this is super helpful because if you need to run like the same command on 11 different matrices that are 1,000,000 elements each, you only need to compile it once, and then you have this mega fast compiled version of the code that's super optimized that can just be run over and over again. So you'll see when I run this, well, you can see the answer, but here comes the answer again. All right, so when we call it the first time, it's actually like there's Python code that is tracing the thing. So it prints out this I'm being traced thing. The second time, we're calling it with an array of the same shape, and we don't see that I'm being traced. So it's just using the compiled version and not the Python version. And then again, in the third time, it needs to trace it again. It needs to recompile it because we've got an array of a different shape. So this understanding of like understanding of JAX just boils down to understanding when JAX is going to trace your objects, how it's compiling things, and whether that is going to end up being faster than the compilation process itself. Okay, so yeah. Okay, so we're going to next look at the speed up that we can achieve using JAX. So all we're doing here is defining this SALU function, which is really commonly used in machine learning. And then we're going to compare the time it takes to apply this object, to apply this function to a particular range of values with and without the JIT compilation. So we've actually changed the syntax a little bit here. I'll just point out that we haven't used the jax.jit decorator, but that's exactly equivalent to just defining a new version of the function with the jax.jit like decorator now instead as a function operating on the function definition. Okay, so I ran these already, and you can see that without the JIT compilation, we've got a much slower code, and with the JIT compilation, it goes much faster. Yeah. Another fun outcome of JAX and understanding JIT is that often when you do these time it things, you get these messages of like the time it function gets mad at you because it's like all of these trials were not consistent times. Like one of them took a lot longer than the others, but that's actually totally consistent with our understanding of JAX because the first time is being compiled, so that's going to take longer than all the subsequent calls. Another important thing is that this speed up is not necessarily going to come into place if you're not actually, using the code, using this function over and over again. So this is just testing the compilation time, this time it statement, because we're only running it once. And you can see that that's significantly longer. It's like 30 times longer than the average time for the JIT compiled thing. And that's because this is the compilation time plus the time to execute. So this is this trade-off that we've been discussing in practice. So a couple of important limitations to keep in mind when you're thinking about JIT compiling your JAX code is that not everything can be JIT compiled. And in particular, JAX is a purely functional language, which I'm going to talk about a little bit in a sec. But basically that means that it can't depend on the state of your input. It needs to run the same no matter what the input is. So in this case, I've defined the exact same functionality as in the previous code block. I'm just calculating this function that's useful in machine learning. But here I've added a Boolean statement that depends on the particular value of x. So when we run this, we're going to get an error. So just set up this try except statement so it doesn't actually cause an error. It just prints out the type of the error. Whenever you have a value that is abstract, meaning that you don't you're not going to know what the value is until you actually run the code, JAX can't condition on that or do higher order functions on that. Yeah, that was all I wanted to say about that. So all that said, the actual syntax of using JAX is pretty straightforward, and it's designed to be as NumPy-like as possible. This is a good and bad thing because if you want to do something in NumPy, you can just try the JNP version of it and it'll probably work. The bad thing is that sometimes you'll have different behavior, so you have to sort of watch out for that. But here are some examples of here's an array. We're defining an array in JNP. And same thing here. Another sort of gotcha is that the standard float size is 32 bits in JAX, which is a decision that was made because this was specifically for machine learning, which typically doesn't require 64 bits. But in scientific applications, we generally want 64 bits. So you can, a lot of JAX tutorials, you'll see this statement at the top of the tutorial that sets the default bit size to 64.
So to go back to the previous example where you had it wouldn't compile because it doesn't know what the type of X is. Can you add something to the decorator to tell it this is going to be a float?
Yeah, so good question. So the question was, can you add a decorator or something to say this is going to be a float? No, because it doesn't depend on the fact that it's a float. It depends on the fact that it doesn't know what the value is. So basically, yeah. No, thanks. That's a really good question. So JAX basically doesn't know how to compile this because it's saying okay, do I compile this version or do I compile this version? I don't know which version to compile because it depends on the exact value of X. Yeah, very good question. Thanks for clarifying. Okay, so I've now mentioned this purely functional phrase a couple times, and I think Jason mentioned it this morning too. So yeah, what I mean by pure functions is that the return value is solely determined by the input parameters, and it has no side effects. So side effects are something I'll just give you a quick example. If I pass in an X array, and then I say x1 equals 0, and then I run this on some x, on some defined value of an array. If I then if I'm running this in pure Python and I were to print out this value of x, this would, x would change. The value of the first element would be modified. So JAX does not allow that. It doesn't allow anything. The function must only operate on the function inputs and not change anything in memory. It can create new objects, but it can't modify any existing functions. So let's take a look at one of these sort of gotchas where JAX actually behaves differently than NumPy. So let me walk you through this code carefully. So we're defining a function to sort an array, and we're passing in an array. Crucially, this can be either a NumPy array or a JAX array. And then depending on we're also passing in a library name. This is just for the print statement. It's not actually going to affect the code at all. And then we're going to sort an array, a NumPy array, and a JAX array. And we'll see what they do. So for NumPy, when we pass in this array of 2, 1, 0, and then call r.sort, and then assign that value to the returned, the output of that operation, what you'll see is that the returned array is actually none. So this r.sort operates completely in place, meaning that it's only going to affect the array itself. It's not going to return anything. But for JAX, that's not possible. We can't modify anything in memory. We have to create a new copy of a function, a new copy of the array, and return that new copy. So you can see that when we're running it with JAX, the original array remains completely intact, but we've now returned something that is the sorted value of the array. So JAX is never in any circumstances going to be able to modify something in memory. And even if it looks like it is modifying something in memory, it's what people like to call syntactic sugar, meaning that it's looking like it's going to modify it, but it's not actually doing it under the hood. So here's an example of how you would do in-place array modifications, in quotes, because that's not actually happening under the hood in JAX. So in NumPy, you would just do xold equals 1, and that would modify the 0th element to be 1. But in JAX, what we're doing is we're first locating the value of this of the xold array at 0, and we're saying I want to set that value to 1, but then we're returning an entirely new array that's a copy of that old one with this value set. So you can see that xold, even though we've done this whole thing that in NumPy would actually modify that in place, it remains the same, and xnew is what's been returned. Another really annoying seeming thing when you first get, oh, sorry, there's a chat message that I missed. So you can't redefine variables with JAX. That's a really good question. So you can create a new variable, but yeah, you can't redefine, you can't overwrite the value of an old variable, because that would be changing a variable in Python is basically just a pointer to a piece of memory. So you can't change what that pointer is pointing to. Yeah, great question. Sorry, I missed that. That was 3 minutes ago. Okay, so another kind of annoying thing that JAX does, seems annoying when you first get started, but actually ends up being being helpful down the line, is that JAX will totally just give you a value if you try to index something that's out of bounds. So for example, in NumPy, if you tried to access the 11th element of this 10 element array, it would give you an error. JAX will just do that. It'll just say, okay, that value is 9. Don't try too hard to interpret why it said 9. It'll just it depends on the operating system, how it's actually gonna decide which value of memory, which value to get from the memory. So if you want to specifically watch out for these out of bounds errors, if you want a specific behavior from your code, if you do access something from memory that's out of bounds, you can use this long, complicated looking syntax of I'm going to try to access the 11th element, and then I'm going to say, okay, if I can fill in some value if I don't end up finding it, and I can fill it in with nan. So if you wanted to fill it in with 12 instead, it'll fill it in with 12. So you can fill it in with whatever you want. Yep.
If JAX doesn't rewrite elements that are stored in memory, does it have a risk of running out of memory?
Yeah, totally. And actually, I ran into memory issues pretty quickly when I started to work with JAX. Python will Python's reasonably good at protecting you from memory issues, but JAX will expose you to them a lot more readily. So yeah, it's something to definitely keep in mind, especially since you're creating copies of things a lot more. It's something that you have to think about a lot more with JAX. Yeah, good question. All right. So now I'm going to talk, I'm not going to talk in a super big amount of detail, but I just want to point out that these two higher order functions exist because they're very helpful for a lot of scientific applications. The first thing that's worth pointing out is that JAX does automatic differentiation. And this is really helpful because calculating gradients is a necessary thing for a lot of optimization algorithms. So there are a lot of like MCMC algorithms and like, you know, things that are the equivalent of like scipy dot optimize dot minimize that are either faster or just require you to know the gradient of your function. And me, as someone who works with Kepler's equation all the time, you know, used to be annoyed by that because I don't know the gradient of Kepler's equation. But now I'm happy about it because you can do it numerically and automatically with things like jax.grad. So this allows like even non-analytic functions where you can't analytically compute the gradient to still take advantage of these algorithms that use the gradient. So I'm not going to go through this, but you can refer back to it if you want. This is just like how jax.grad actually works and is implemented. And one nice feature of this that is worth pointing out is that you can compose it as many times as you like. So you can compute like second and third derivatives with jax.grad as well. Another really nice thing that JAX does is automatic vectorization. So if you've ever used the map function in Python, where you basically like you map a particular function on like over several parts of an array, JAX has an analogous thing called jax.vmap, which will compile and then apply your function in the same way. So I've got an example here that I'm similarly not going to go through right now, but I encourage you to look through to sort of get a sense of like how the syntax of jax.vmap works, and then also, you know, what it can actually do for you. And also I should say that this often using jax.vmap smartly is not a good word. Using jax.vmap in a way where you understand what it's doing underneath the hood will often lead to computational speedup. So it's a good thing to sort of keep in your tool belt when you're thinking about JAX. All right, the last thing I want to say before I set you loose to do some activities is a very quick sentence about running JAX on GPUs and TPUs. The reason that it's so quick is because it's pretty easy to do. If you are already running JAX, you can probably already run it on GPUs or TPUs. So one quick thing to say is, what are GPUs and TPUs? So we got a little bit of an intro in the last hour, and you're going to get even less of an intro here. But basically, GPU stands for graphics processing unit, and TPU stands for tensor processing unit. So these are both pieces of hardware. So it's either like you have it in your computer or you don't. You can't like do something in your software that will like, you know, allow you to run code on GPUs. But they were designed for different particular applications. GPUs are older than TPUs, and GPUs, as the name implies, were designed for running graphics. So you can imagine that in graphics applications, like in video games, you have like, you know, if you have to do, I know this is probably not done in a lot of video games, but if you need to like trace rays of like 1,000 rays at once, you know, trace them through an environment. You can imagine that if you can like change your hardware to do these computations all at the same time, that'll massively speed up your piece of software. TPUs are tensor processing units, and these were originally designed at Google for doing machine learning. When I showed this lesson to Jason, he kind of laughed that I was even like making a distinction. He's like, yeah, it's all like hardware acceleration. It's the same thing. But I did an internship at Google, so I really like drank the Kool-Aid of like, oh yeah, TPUs are so cool. They're so much better than GPUs. And people are like, why? And I'm like, I don't know. They're faster. But yeah, basically they're the same thing. They have different optimizations. If you're really getting into it, you'll learn about it. So a critical advantage of JAX is that you don't need to change any code in order to run JAX on a TPU or GPU. In this activity, you're actually going to run code on TPUs and GPUs. And one really nice thing about Colab is that you can do this very easily. I'll show you how to actually do it. Why can I not see the... I think I hid oh, there it is. Oh, thank God. I was worried. I was like, where did it go? So if you go to runtime up here and then change runtime type, you can select the type of hardware accelerator that you want to use. So by default, Colab will run things on CPUs, but you can also select GPU. It'll like remove all of your variables and stuff, so you have to like redefine stuff or rerun stuff. The TPUs are sometimes not available. Oh, it looks like there's one available right now, so that's good. But yeah, don't be surprised if like you can't run it on a TPU. But yeah, so for this activity, I would suggest just running it on a GPU because those resources are typically more available. But yeah, you should also feel free to play around with TPUs if you can get access to one. Yeah, so this is the first activity will be exploring JAX's performance on CPU versus GPU. And then the second activity, you can tell I was getting tired and a little lazy writing tutorials, but I was like, here, look at this other tutorial. But to be fair, this is a very, very good tutorial in my opinion, and you can read through it and try to learn about NumPyro, which is a library built on top of JAX to do Bayesian model inference. All right, so I'll give you probably until like 57 after, so like 17 minutes. And then I'm going to show you a plot of the answers to one, so we can. So I'll post the lecture activity, the solution afterwards, so you can see how I did it. But I want to make sure I talk through like the implications. Okay, so I'll show you these plots. So this is the plot that I made for array length on the CPU. So this is no JIT compilation, and this is with JIT compilation. So you can see a couple of things. First, that the level of the time is relatively flat, modulo some like small number statistics for the array length over here. Also note that this is log 10 of array length, so this is like an array of length 10, 100, 1,000, so increasing by a order of magnitude each time. So you can see that for both the JIT compilation and the no JIT compilation, the execution time is about the same, and that's just like the time it takes the code to run, not the time or the time it takes like the code to like be compiled and actually like execute. So the array, like the like actual evaluation of the SELU function doesn't really start meaningfully contribute to the runtime until we get to these larger array lengths. And you can also see that the JIT compilation adds like this almost like constant factor of speed up at all array lengths. When we connect to the GPU, this is what our time ends up looking like. So we still get this sort of almost like constant speed up from the JIT compilation. But overall, the performance is a lot more linear. So like there's no significant, decrease in performance on the GPU for even these very large arrays. At a certain point that will turn around and we'll start getting increases again. And you'll also see, like, I probably should have put these on the same plot, but 10 to the minus 3 here is about here. So you can see that for these smaller arrays, it's actually more efficient by a lot, by orders of magnitude, to run it on the CPU and not on the GPU. And that's because the process of actually like sending the code to the GPU and sending it back once it's done takes a significant amount of time. And the difference between that, the GPU execution time and the CPU execution time, is directly like how much time that took. But you can see for these large arrays, this like exponential increase is very quickly going to be beat out by this like roughly constant time evaluation on the GPU. This is also sort of a non sequitur, but I found this to be a moderately interesting software design problem because we had to like connect to a GPU, connect to a CPU, like save intermediate values and stuff like that. So I think after doing it, I would probably do it a different way. So what I actually did was I just had like different versions of these things run. Or where am I actually looking? I just like had, these comments to myself like, oh, I ran this code when I was connected to a CPU. I ran this code when I was connected to a GPU. I did define this function to abstract away some of the functionality that I was going to repeat over and over again, which I thought was good. But I think if I were doing this again, probably what I would do is save the values to like a CSV or something, and then have a separate like maybe even a separate notebook that reads in the values and like makes the plot all together. So separate out like one notebook for GPU evaluations, one notebook for CPU evaluations, and then one for reading in the results. Because this design is very prone to user error. I'm assuming that the user knows like, okay, now I'm gonna change the runtime to CPU. Now I'm gonna change the runtime to GPU. And I think it would be a lot easier if I separated out those things. Okay, so since this is a workshop on software design and development, I figured I would throw that in. But yeah, okay. I think that's all I wanted to say. Any questions? Yep.
When I was like playing around with it, I just like kind of changed where like the JAX is implemented to like the same way that you had it was there, like the hot kind of diction. And it seemed like if you sped it up a little bit, is that possible? Or like do you run that?
Yeah, so the question was that Zoe, rather than using the Salu JIT here, which I'm pretty sure was defined with like the JIT function being applied to Salu rather than the decorator, I wouldn't think that that would change the actual evaluation, but I'm not sure. So it's totally possible that that is more efficient, but in my mind they're the same thing, so I'm not sure. Worth checking. Good question. Yep.
So it kind of seems like JAX is like a bit better. Are there any situations where like you want to use JAX, you'd rather use NumPy?
Yeah, it's a good question. So the question was like, why wouldn't you always use JAX and instead of NumPy? I think there are a couple of reasons. Well, I think we've seen a lot of the advantages of JAX, so I'll focus on the disadvantages. JAX is, I think, first of all, it's a lot newer. So if you want people, there's a non-negligible like advantage that you get when you're a software developer to making your code easy to run and easy to develop. So if you want like lots of other people to be contributing to your code and making changes, like having tools that everybody's sort of on the same page with is like a non-negligible benefit. I think JAX is also, JAX will also like, we've seen here that JAX's performance is really dependent on your hardware. And so not everybody has access to a GPU. And so if you want, it depends on your application. Like if you're writing code that you want to, be ultra performant and run on, a very expensive high-end machine, then yeah, you want to spend all the time you can like making your code really, really good. But if you're like, Astro, for example, and you want your code to be directly accessible to a large group of people on a large variety of setups and stuff like that, then like implementing everything in JAX doesn't really make sense. So there's a general like trade-off in software development between performance and understandability. Generally, ultra-performant code is hard to read, and so it can be hard to like debug or add things to. Yeah, it depends on what the application is.